So am I audible, right? Perfectly.
Yes, sir.
Okay. Thank you. Okay. So let's start with the today's class. And what we were doing in the last session was we were just trying to identify the uh, critical points. Okay, critical points for functions of two variables f of x over y, and we do have verified that in this case, interior extremum theorem tells you that critical points will be those points where simultaneously fx and fy vanish whenever they exist. Okay, if they don't exist, okay, then so there are the point a comma b such that fx equals to 0 and fy equals to 0 at points a comma b. And another points, the points who have some c comma d, where either fx or fy or both do not exist. So then you will say those points are critical points. Okay, and then based on the nature of the function, we will decide the whether the point will become the local maxima or local minima based on the definition that if you are able to identify an open disk, okay, where all of the values of so let's say that you are able to find a disk D, which we denote, okay, D and disk centered at disk centered at critical point, okay, critical point, let's say x1 or x0 comma y0, because we don't know where is either this case or that case. Okay, it is centered at critical point x0 y0 such that what we have is, or this on this disk, if you have f of x comma y is less than equals to f of x0 comma y0 for all x comma y in that disk, then you say this is a, then it implies x0 comma y0 is a local maximum because it lies above all the values, local maximum. Okay, or if you have f of x comma y is greater than equals to f of x0 comma y0 for all x comma y in T, then this implies x0 comma y0 is a local minimum. So we had also identified one more classification, which was known as saddle point. Okay, means if you are not, so here you are able to identify a disk. Okay, if you are not able to identify any disk such that either one of them happens, okay, then means for every disk, whatever you will take, centered at, so just let me see. You have another case, this is the very final one, is about the saddle point. But we have learned that if uh, if you have for every disk, if for every disk centered at x naught comma y naught. If for every disk centered at x naught y naught, there are, and say let's go to the next page. So uh, uh, there are points x comma y such that f of x comma y is less than equals to f of x naught y naught for some values, and f of some x comma y is greater than equals to f of x naught comma y. Both are case put together. Okay, there are points x comma y such that in that disk, okay, that you can because it's for every disk, you can name it as uh, because we have already taken the particular D here. So for every disk, let's say this is D1 centered at x naught y naught. So there are points x, y in D1 such that for some points f of x, y is less than equals to f of x naught y naught and f of x, y greater than equals to f of x naught y. Okay, so this is the situation like this. Okay, you have this point, okay, where you will be able to identify a disk where you will have certainly upward and downward points. Okay, right. So this defines saddle point. So such critical point, such critical point is known as saddle point. So this is what we have learned in the last session. Now, likewise, in the function of single variable, we have seen there is a second derivative test. Okay, we do also have the second derivative test for this case as well. Okay, there also that was the application of Taylor's formula. Okay, here also it will be the application of Taylor's formula for function of two variables. Okay, right. So that we will see if time allows. We will see that part, that how it will becomes the application for of a Taylor's formula. Okay, that we will see if time allows to us. Okay, but let's understand what will be the derivative, second derivative test for knowing that the critical point is going to be a maxima or minima or a saddle point. Okay, right. So again, when you talk about the second derivative test, means a function must be all first order partial derivatives, second order partial derivatives must exist and continuous. So the such conditions has to be there or has to be checked. Okay, you have to check that first. So here is the second derivative test. It says that suppose, as mentioned, that f and its first and second partial derivatives are continuous throughout a disk centered at AB. Okay, so you have a disk centered at AB. Okay, let's say this is D, over which this f and its all first order and second order partial derivatives are continuous. And that AB is a critical point. Okay, that's what. So if they are received, because f and its first and second order partial derivative continuous, means they exist at every point inside the disk. So certainly when you talk about that, when you mention that this point is a critical point, means that both fx and fy must be zero. Okay, so that's obviously true when you say that AB is a critical point. Okay, for AB to be a critical point, it has to be there. Okay, vice versa, whenever the first order partial derivative exists. Okay, now then what you need to identify is the sign of this first. Okay, it is written in some other direction, but you have to identify the sign of this number. Okay, sign of this number, which is again and again mentioning in each bullet here. Okay, and if you try to understand, this is nothing but the determinant, or is also known as Hessian matrix. Okay, determinant. Okay, so where this is a 2 cross 2 fxx, fxy, fxy, fy. So I have taken here fxy and fxy here. Okay, why? Because here second partial derivatives are continuous. So mixed derivative theorem tells you that fxy or fyx both values are the same. Okay, so we are not worried about which order you could perform to find out the partial derivative of f with respect to x and with respect to y. First with respect to x, then with respect to y, or first with respect to y, then with respect to x. Because mixed derivative theorem guarantees that fxy or fyx both will be the same. So you have to check when you are performing the second derivative test, you have to see this, this is a determinant, okay, of a Hessian matrix known as Hessian matrix due to some reasons. Okay, so that may be clear when you look at some applications. Okay, so this is so discriminant also. This is also known as discriminant. Okay, so there are various name attached with this quantity. Okay, so if you find out the determinant of this matrix is nothing but fxx into fyy minus fyx. So you have to check the sign of that determinant. Okay, so if that is positive, greater than 0, okay, then you can talk about either maxima or minima. If it is negative, you can tell certainly that saddle point. If it is 0, so maybe case that this Hessian determinant of the Hessian matrix is 0. That point means at that situation the test is inconclusive. Okay, so what we observe as follows. So if that means, see, whenever the sign of this quantity is greater than 0, okay, what will happen, that this theorem suggests you that if you have, this is fxx into fyy minus fxy square is greater than 0. What it says, so fxy is a surface, right? Okay, fxy is a surface. Okay, in the you have this f of xy is a surface somewhere. Okay, now if it is greater than 0 at a point AB, we are talking about at point A comma B. Okay, so what is happening here is this, from the point AB, it will move, it will go in the same direction, either in the downward direction or in the upward direction. Okay, only two possibilities there. So if it is a downward direction, then it attains maxima, and when it's an upward direction moving, the surface is like that here nearby, so it is a local minimum. So so how to decide that is a downward or upward? It depends on the sign of second derivative fxx at AB. If it is less than 0, it is going to be the downward. If it is greater than 0, it is going to be the upward curve. Right? Okay, so this is what here is happening, and whenever you have this in the case this quantity is fxx into fyy minus fxy square is less than 0, then you can't decide. Okay, from the point you have maybe have this and along the curve this. Okay, so it has some upward and downward, both the things are going. Okay, you take any disk again in the same fashion. Okay, right. So there is no other way. It's like it will not move in the same direction. It will have different directions. Okay, so that point is a saddle point. And equals to 0, you can't decide Okay, because of again that you can see in the application of Taylor's formula why it is happening. Okay, for equal to 0, why the test is inconclusive. Okay, so that we will see if the time allows. So as we have mentioned you when this local maxima and local minima, let's read this and this complete lecture now. Okay, so you have a f has a local maximum at AB if these two things together will be true. Okay, means the whenever, so you have to check for the, so I will just now try to give you the gist of this result. Okay, how to apply this result. Okay, so very first thing is you have to check the continuity of f, its first and second partial derivatives. Okay, try to collect all the points AB where this fx and fy both will vanish. So those points are critical. Then you have to check the sign of this quantity, okay, that determinant, or okay, fxx into fyy minus fxy square, the sign of this. Now, if this is greater than 0, then you can say local maxima or local minima. If it is less than 0 at that point, you can say saddle point. If it equals to 0, then test is inconclusive. Now, if that is greater than 0, then you have to check the sign of fxx, the second derivative of f with respect to x. Okay, so if the second derivative of f with respect to x is a negative, then you say it is a local maximum. If it is positive, then you will say it is a local minimum. Okay, right. So I think this part is clear now how to apply this test. So let's look at one example here. Okay, so let's try to identify the local extreme values of this function. It's given to you. Now, so you are given with f of x comma y is equals to x into y minus x square minus y square minus 2x minus 2y plus 4. Now, this function is a nice function. Okay, the right hand side, it is easy to verify that this function is continuous. It's a type of a polynomial, right? Polynomial in x and y both. You have only positive powers. Okay, so it's a combination of continuous functions, sum of continuous functions, constant, 2y is continuous, 2x is continuous, y square is continuous, x square is continuous, x into y is also continuous. So sum of continuous function is continuous. So you can apply any rule which you are comfortable with. Okay. Now, moreover, you can also identify what is fx. It has, if it is a type of polynomial, you can talk about it has all further continuous derivatives. Okay, if it is a polynomial type. Okay, so from here I can certainly derive what is fx is going to be y minus 2x minus 2. What is fy is going to be x minus 2y minus 2. So this first order partial derivatives are also continuous. You can also verify that. Now, third thing is you have to see the second, because you want to perform the second derivative tests, fxx. What is fxx? Is minus 2. What is fyy? Is also minus 2, that constant. And what is fxy? You will see here whether you identify fxy or fyx, both will be the same, that is equals to 1. So all are constants, again continuous. So all of the conditions of the second derivative test is verified regarding the continuity of first order function and its first and second order partial derivatives. Further higher order derivatives are 0. Okay, that you can also verify. Okay, right. Now what next is you have to identify all the critical points. So for possible critical points, possible critical points, fx equals to 0 and fy equals to 0. Okay, now what is fx? This is implies, so fx was y minus 2x minus 2. So y minus 2x minus 2 equals to 0. And this fy is by symmetry x minus 2y minus 2. It has the same. Now you have two equations in two unknowns. Both should do 0 together. Okay. So from these two equations, you can certainly identify what is x and what is y. Okay. So you have these two equations now. X minus 2y equals to 2. And you have minus 2x plus y equals to 2. Now you multiply it by 2 and add. What will happen is going to be just 2x minus 2x. That's you are going to add them, right? So minus 4y plus y is minus 3y is equals to 4 plus 2 is 6. So y is equals to minus 2. And so y equals to minus 2. So you can use any one of the results. So I am using this x equals to 2y plus 2. So it's minus 4 plus 2. So that's going to be minus 2. So this gives you the only possible critical points. So this implies only possible critical point is the point minus 2 comma minus 2. There are no other points, critical points, because because other critical points are the points where the first order partial derivatives do not exist, either one of them or both of them. But that is not the case. So only possible critical point is this. Now, also fxx at minus 2 comma minus 2, I can find that's going to be, what is that? Fxx is minus 2, constant only, right? So at minus 2 it is also minus 2. Fyy at minus 2 minus 2, that is also minus 2. Fxy at minus 2 minus 2, that value is 1. Fxy is 1. Okay, so that's a constant, so it will not change with respect to any point. Now, this certainly implies, fxx into fyy minus fxy square, that is equals to minus 2 into minus 2 into minus 1 square is equals to 4 minus 1, that is 3, that's greater than 0 at minus 2 minus 2. We are talking about specifically at this point. So this is a greater than 0. Okay, this is greater than 0. The sign is positive. So this tells you that now it has either maxima or minima at that point. Okay, so now fxx at minus 2 minus 2, that is equals to minus 2, and which is less than 0. So second derivative test theorem tells you that implies f has a local maxima at minus 2 minus 2. And the maximum value is, f at minus 2 minus 2. So that's equals to, what will be the value? F at minus 2 minus 2 is, from here, okay, x equals to minus 2 and y equals to minus 2. So first term, minus 2 into minus 2 is 4. Minus this is 4. This is minus 4. Minus 2x. X is minus 2. Right? So minus 4 minus minus 4 plus 4. So 4 will get cancelled. Minus 4 plus 4. So that will also cancel. Right? And this is plus 4 and plus 4. That's going to be 8. So the value of f at minus 2 minus 2 is, maximum value will be the 8. Okay, and what will, so this is going to be, if you try to identify this, okay, somewhere you have, this is X, Y, and Z. So X equals to, say here is, this is negative side, this is negative side. Okay, somewhere -2 in that plane. Okay, so in that negative side here, okay. So here is going to be the f at -2 is 8. So z equals to 8. It will, from nearby, the curve will be like this. Okay, so here z equals to 8. We have the value at f at -2 is 8. Z equals to 8. So this is going to be nearby, will be the downward. Okay, because it has a local maximum. Okay, right. So this, you can certainly identify the nature of the surface, okay, in some nearby. Okay, this in the some means locally. Okay, not that globally. Maybe afterwards it may go further above like that. We don't know, but near this it's going to be that. Okay, right. Now, what is next? Okay, so now
Sir,
yes.
sir, can you again explain why, how we are deciding that by sign means the determined value is positive, then how we are deciding? You are explaining no in the diagram.
Means, where?
Yeah, in the diagram.
Sure.
Sir,
Here,
yes, yes, sir.
our deciding this you're talking about.
Means the theorem is there, but how it is means if it is positive, then how it is maxima or minima, and if it is negative, means there should be some means logic. No, you are saying something, but I didn't get that.
Okay, if I'm getting you correctly, okay, what I understood from your point is you want to understand how I'm deciding is going to be downward and upward
Yes, sir. Yes.
near that point.
Means maxima is there, therefore it is downward. That I
Downward.
getting, but
Ah,
how from the sign we are getting that? Because in function of single variable it is understood because it is slope.
yeah. So this is what is okay. So that part you are getting right. There's no problem in that, right? Only
Yes, sir.
problem is what you're understanding whether greater than 0 or less than 0. How you're mentioning that greater than 0 will tell you that it's moving in the same direction in all the way.
Yes,
That's
sir.
what it meant, right?
Yes,
Okay.
sir.
So again, this needs to, again, I'm telling you this because of the Taylor's formula. Okay, so Taylor's formula will tell you that this is going to be, so maybe I may give you a hint here. Okay, so Taylor's formula tells you somewhere that this it's going to be purely depends on the sign of this. I just this is a second. I need to say is so that not define the Taylor's formula function of two variables. How to get here is this is means okay. So if you have let's take a b is a point and another point is let's take small increment in both the direction b plus k. So this is what is happening, right? Small increment whether in in the negative side downward or upward, we don't know. Okay, right. So you want to look at the sign of in the neighborhood, right? So it means you will see the change here. Okay, whether it will be positive or whether it will be negative. Right? Okay, so this is going to be highly depends on, in that, I may say that it's going to be, it leads to that a very, I'd say here is a positive constant somewhere. I can only give you right now that very first thing is the first term will come out as like a positive constant at that point. Plus you will have this quantity will be sitting fxx into fyy minus fxy scale time some k square here will come into the picture. So here is a positive term always greater than 0. Okay, so this is this will be highly depends on here. So if it is positive, so this completely is positive. Did you get my point?
Yes, sir.
Okay, so this change, okay, which you are trying to identify in the disk, okay, because at the point AB, okay, you have it in the disk. This is a critical point, okay, and you are moving in some direction, okay, any direction. So you took any point. So it's a small increment somewhere a plus h over b plus k. You are looking nearby, as small as possible. You can look at the disk as well. So you are looking at whether it lies above or lies below. Okay, right. So this means you are looking at the difference of these two values. Okay, if it is greater than 0, means you have f of a plus h over b plus k is lies above f of ab. If it is less than 0, it is lies below f of a. Okay, it will move either, it will only be, it's only one way possibility. Okay, whenever you have the greater than 0 here. Okay, somewhere here it's also is going to be somewhere it is going to be multiplied by here fxx as well at the point. Okay, so here it is means I'm just talking about in that here this is going to be mathematically that relation will hold true. Devashi, I can only tell you at this point this much. Okay, this is positive quantity. I think you must be agree with this. If this positive, completely positive, this will tells you that it's going to be greater than 0. Whenever fxs is greater than 0 and less than 0, that's going to be the secondary part. Okay.
Okay,
I
sir.
think that. Okay, and if
Yes.
it is negative, means somewhere it is going to be means for sufficiently close hk, you will be, there are some values where it will be negative or where it will be positive. And when you have this is equals to 0, you can have this is always a positive and maybe 0 as well. So we don't know what can happen. Okay? So that's why the test remains inconclusive whenever this quantity will be 0. Okay.
Okay, sir.
Right. Okay. So, like in the case of single variable, okay, we are trying to identify absolute maxima and minima there. Similarly, in that case, in this case as well, we can talk about absolute maxima and minima. So whenever we are talking about absolute maxima and minima, we are certainly talk about on a closed and bounded region. Okay, unbounded region we are not considering here. Okay, it may have absolute maximum or it may have absolute minima, like a downward bound, infinite, okay, in an unbounded region, or upward bounds, okay, on sitting on the xy plane. Okay, it has absolute minima, upward bound, right, and it will have, okay, it will have the absolute maximum minima at 0, 0, you can say, okay, wherever it intersects the xy plane or touches the xy plane. Okay, that point it will be having absolute minima, but we can't take always the unbounded regions. Okay, so for talking about absolute maxima and minima, we are certainly talking about one of closed and bounded. That's the very first thing. Okay, now for finding the absolute maxima and minima, certainly at a point we are talking, so we have to collect all the possible critical points. Okay, so the possible critical points are the very first thing is the interior points where f may have local maxima and minima. That's the very first. Okay, you have to point all the possible interior points where f may have local maximum. So you have the interior extremum theorem, okay, which says that if f has continuous first, if f has all first order partial derivatives, okay, so and if it has local maxima and minima somewhere, then both fx and fy will be zero. If they do not exist, those points are also the critical points. So you have to list out all those interior points and also corresponding their values, f values at those points. Okay, list out all these things. The second thing is the boundaries are also the critical. Okay, so you have to search along the boundary as well. Okay, of the region R. So it depends. R is the rectangular region or triangle region or some uh, uh, okay, or some hexagon or somewhere. Okay, it's what kind of shape it is. Okay, circle or something. Okay, so list all the boundary points of R where f has local maxima and minima and evaluate f at this place. Again, you have to repeat the same story here. The only point here is you have to look at the fence, okay, or you can say boundaries, okay, closely and try to identify what are the possible critical points, so that you will sooner now know once we solve an example. Okay, now then what you have to do, the final step is you have to look through the list for the maximum and minimum values of f, and that will be which will be the maximum value, that will be the absolute maximum, and which will be the minimum value among them. This will be going to be the absolute minimum. Okay, right. So the steps again will be clear by looking at one example. Okay, so let's try to see this example, which says that find the absolute maximum and minimum values of this function on the triangular region in the first quadrant bounded by these lines. Okay, okay. So it's given that, okay, let's try to identify f of x comma y is equals to 2 plus 2x plus 2y minus x square minus y square. Now, the very first thing is it is easy to verify that this function is a nice function. Okay, and all first order, second order partial derivatives exist and continuous. That's very easy. And you can also certainly find out what is fx here is 2 minus 2x. What is fy is 2 minus 2y. What is fx? X is minus 2. What is fyy is minus 2. What is fxy? Mixed derivative theorem is also applicable here. So fxy is 0. Okay, so okay, we have to list out all the possible critical points. Okay, now for critical points, so for possible critical point, critical points, we must have fx equals to 0 and fy equals to 0. So this tells you that 2 minus 2x equals to 0 and 2 minus 2y equals to 0. This both will give you x equals to 1 and y equals to 1. So this implies the point 1 comma 1. The critical point. So by first derivative test, you are identifying the critical point of this surface. Okay. Now, what you are interested in the absolute maxima and minima on the rectangular region R. What is the rectangular region R is bounded by the line x equals to 0, y equals to 0, and another is okay, just let me restart this. and y equals to 9 minus x. And y equals to 9 minus x. So you have this triangle region, okay, bounded by the line x equals to 0, y equals to 0, and y equals to 9 minus x. So x equals to 0, y is 9, and y equals to 0, x is equals to 9. So you have this triangle. And you have to see that the critical point, what you have observed is 1, 1. Let's say these are the points O, A, B. Okay. Now, this is the line y equals to 9 minus x. This is your y equals to 0. And this is your x. Now, you have to certainly verify that whether 1, 1 lies inside this region or outside. If it is outside, we don't bother. That point will not be the part of that list. Okay, but here you can here it's going to be this is somewhere point is here inside point 1. So y equals to x. Okay, so y equals to x will cut down this equation at the point 9 by 2 comma 9 by 2. Okay, and certainly 9 by 2 is greater than 1. So you can easily decide that 1, 1 is an interior. Okay, so first you have to verify that critical point is an interior point or not. Okay, or you have to discard those points which are not with the interior point of this triangle. Now, so we have already listed 1 point, 1, 1. That's going to be the critical point. Okay, and moreover, you can also see here on the critical point, the interior point. So now you can check that fxx at 1, 1. So these are constant values -2, -2, and 0. Okay, so I'm again mentioning fxx at 1 is -2, fyy at 1, 1 is -2, and fxy at 1, 1 is 0. So this implies that that determinant of the Hessian matrix, that's fxx into fyy minus fxy square, is equals to 4 greater than 0 at 1, 1. And now fxx is -2, which is negative. So it has a local maximum at point. Local maximum, but not the minimum. But not the absolute. Okay. Okay. Also, fxx is equals to -2, which is less than 0. So this implies f has a local maximum at 1, 1. And what is the value of f at 1, 1? Because you have to collect that as well. So that's going to be 2 plus 2 plus 2 minus 1 minus 1. So this 2 will get cancelled and that's the 4. Now, but you are in search of absolute maximum, okay, in the entire region. So you have to move along the boundaries. Okay, so here one of the boundary is you can move along the line OA, along the line AB, and along the line OB. Okay, you have to search out the critical points along that line boundaries. Okay, so along OA, what is OA is y equals to 0. Now, what is f of x comma y? If you recall, that is 2 plus 2x plus 2y minus x square minus y square. So along the line y equals to 0, what is f? F is x comma 0. That's going to be 2 plus 2x minus x square. So it is a function of single variable when you are moving along y equals to 0. So you can now work out like this. You can say this is a some g, and you find out all the for critical points now. So for critical point, so for critical points, g dash of x must be 0. Okay, because this is a polynomial and it's a differentiable, derivative does exist. So now what is g dash of x? That's going to be 2 minus 2x equals to 0. This implies x equals to 1. Okay, so now, so this implies what will be the critical point along y equals to 0, x equals to 1. So the 1 comma 0, so x equals to 1 and y equals to 0 be a critical point. Only possible critical point along the line OA. Now along and also you should not miss the boundary points. Okay, again boundary points where you have sharp edges, so derivative does not exist. Okay, whenever you are talking about these points, these are the sharp edges, okay, where the derivative does not exist. Okay, so those points are 0 0. This is going to be 9 comma 0 and b is a 0 comma 9. Okay, so those points are also critical points. So now, so along OA, what are other critical points are? You have 0 0 and 9 comma 0. Okay, so there are 3 points, critical points: 0 0, 9 comma 0 and 1 comma 0. So another point, interior point is 1 comma 0. This is along OA. Now along OB, you have x equals to 0. So again, you have the same symmetry at 0 comma y is equals to, if I recall, that's going to be 2 plus 2y minus y squared. And that you can denote by hy. And again, you repeat the similar process. So the possible critical points are, the boundary points are 0 0 and 0 comma 9. And other point is going to be 0 comma 1. So this already has been considered, so you no need to consider again. 0 0 is already counted here. So it's not necessary to break here. So only now another point is along AB. So along AB, the boundary points are 0 0, no, not 0 0. The boundary points are 9 comma 0 and 0 comma 9. These are the boundary points, but they have been considered along OB and along OA as well. So there is no point to reconsider them. Only now you have to look at the point where this interior point on the line is whether in between there is any critical point or not. So for that, you have this along AB is y equals to 9 minus x. So along this line, f of x comma y is 9 minus x. So that is equals to 2 plus 2x plus 2y. So y is 9 minus x minus x square minus y square is 9 minus x whole square. So replace everything y by 9 minus x. So this again will be a function of single variable. So 2 plus 2x plus 18 minus 2x minus x square minus, this is 81 plus x square minus 18x, right? So this is going to be, 2x will get cancelled. So 18 plus 2 is 20, 20 minus 81 is minus 61, right? Okay, and minus x square, that is minus 2x square, and minus plus 18x. So you can call this as somewhere like h1 of x. Now for critical points, you have to differentiate and put equals to 0. Okay, so this implies 18 minus, its derivative is 4x equals to 0, and this implies x equals to 9 by 2. So x equals to 9 by 2, what will be the y? Okay, so when x equals to 9 by 2, y is equals to 9 minus x. So that's going to be 9 minus 9 by 2, so that is 9. So along the line AB, the possible critical point is 9 by 2, 9 by 2. So now I will list out all the critical points which we have obtained. 0, 0, 0, 9, 9, 0. These are the boundary points which we have already. 1, 1 is the interior point there. Another point is 1, 0, 0, 1. This is along the line OA, it's along the line OB, and along the line AB is 9 by 2, 9 by 2. So these are all are possible critical points. Now you have to find out all the values at these critical points. So, so f at 0, 0. So let me write down fx comma y here so that it is easy to 2x plus 2y minus x square minus y square. So f at 0, 0 is 2. F at 1, 0 is 2 plus 2 minus 1. That's going to be, right, 4 minus 1, 3. F of 0, 1 is due to symmetry, again 3. F of 1, 1, that's going to be 2 plus 2 plus 2 minus 1 minus 1. That is 4, right? Now, f of 0, 9 is equals to 2 plus 18 minus 9 square is 81. So that's going to be minus 61. Due to symmetry, f at 9, 0 is also minus 61. Another point is f at 9 by 2, 9 by 2. Okay, so 2 plus 9 minus 81 by 4 minus 81 by 4. So that's going to be minus, so you can have 20 minus 81 by 2. So that is going to be minus 41 by 2. Right? I've done the right thing, right? So 2 plus 9 minus 81 by 4 minus 81 by 4. So that's going to be minus 81 by 2. And this is 20. So 20 minus 81 by 2 is 40 minus 81. That's minus 41 by 2. Okay. So now you can look at which will be the maximum value here, the positive value that is going to be, this is the maximum. So f at 1, 1 is going to attain the maximum value. What will be the minimum is you have, this is minus 60. Okay. So f at 0, 9 or 9, 0. So you have 2 points of absolute minimum, 1 point for absolute maximum. So there may be multiple points. There is no uniqueness about it. Okay. Right. Fine. So this is about the absolute maxima and minimum. Okay. Now let's have one more example which may looks more realistic. Okay. So a delivery company accepts only rectangular boxes, the sum of whose length and girth parameter of a cross section does not exceed 108 inch. Find the dimensions of an acceptable box of largest volume. So the rectangular box, how it looks like is you have a rectangular box. Okay, so you have a rectangular box. So let x is the length, y is the width, and z is the height. Okay, now what is the volume of this rectangular box? Volume, if you decide, it's going to be length into width into height, x into y into z. Now, what is given is to you is that delivery company accepts only rectangular boxes, the sum of whose length, girth, does not exceed 108 inch. Okay, so what will be the girth of the cross section is going to be this. Okay, the cross section okay, so the parameter of this cross section is what? This is y, this is y, this is z width, 2 times width plus 2 times height. So that's going to be parameter of the girth is going to be 2y plus 2z. And what is given to you is x plus 2y plus 2z is cannot be more than 108 inch. It is maximum 108. So from here, what you will observe, there are various ways to handle this. So now x equals to 108 minus 2y minus 2z. From here, you will get a one condition. Now, what is the volume now in that case? So v equals to x into y into z. So what is x is 108 minus 2y minus 2z times yz. So it's a function of two variables now instead of three. So 108yz minus 2y square z minus 2z square y. And it is easy to observe that this function is satisfies all the conditions for the second derivative test, all the first order partial derivatives and all. Okay, so Vy, if you try to find out, so that's going to be 108z minus 4yz minus 2z square. What is Vz is for critical points. So this is going to be 108y minus, this is going to be 2y square minus 4zy. Okay, now for critical points, so for critical points, what you can find out is all the possible y comma z pairs such that Vy equals to 0 and Vz equals to 0. So this implies you have two equations in two unknown, right? So you have this is 18z minus 4yz minus 2z square 08z minus 4yz minus 2z square equals to 0. And Vz equals to 0 is 10. So this is symmetry 108y minus 4yz again minus 2y square equals to 0. Right now, certainly you can remove this z here, okay, because here see z can be common here. So z is also common, y is also common in the both the pair. So z equals to 0, y equals to 0 will also be the possible critical point, but that is not favorable one. Why? Because if z is 0 or y is 0, there is no volume. Okay, so z equals to 0 and y equals to 0. This is discarded. So z equals to 0, y equals to 0, with case is discarded. Okay, all the cases. Okay, so only possibility, so you can divide both sides by z now. So this implies, so only possible critical points are 108 minus 4y minus 2z equals to 0. Right? And another equation is y, if I divide by y both sides, so 108 minus 4z minus 2y equals to 0. Now this is two equation in two unknowns. So again, now you can solve this now. So you have this is 4y plus 2z is equals to 108, and you have 2y plus 4z is equals to 108. Now you multiply this by 2 and subtract. Okay, so this will subtract, this will be going to be 0, so it's going to be 8. 2 minus 8 is minus 6z is equals to 108 minus 216, right? So it's going to be minus 108. Okay, so this will get cancelled. Okay, and this is going to be also cancelled, right? 18. So z equals to 18. Okay, so this gives you z equals to 18. And what is y from here? Any equation you can take now. Okay, because these are symmetry, I think. Okay, so what is it's going to be is 4y is equals to 108 minus 2z, so that is 36. So this is going to be so again, this is going to be y is also 18. So this is also tells you that y is equals to 18. So the possible critical point is is 18 comma 18. Now, what is fyy or not fyy, vyy is equals to, so vyy is, if you differentiate again, it's going to be minus 4z, right? So from here, this implies vyy is equals to minus 4z, and this implies vzz is equals to minus 4. And what is vyz also I can find out. So vyz is equals to, differentiate any one with respect to z now. Okay, so I'm differentiating this with respect to z, so it's going to be 108 minus 4y minus 4z. So this is going to be vyz. Okay, right. So now what you have to, so vyy is, if I recall, it's going to be minus 4z. Vzz is equals to minus 4y, and vyz is equals to 108 minus 4y minus 4z, minus 4y minus 4z. Now at 18 comma 18, this point. Okay, so that is going to be vyy is equals to minus 72, vzz is equals to minus 72. Okay, and what is vyz? Is going to be, yes, so 72, right? 108 minus 72 minus 72. That's going to be minus 36. Okay, now at 18 comma 18, so now it is here it will be easy to see that okay, so let me complete this. Okay, so you have, this is minus 4z minus 4y. It's at 18 comma 18. The values are vyy is minus 72, vzz is minus 72, and vyz is minus 36. Now vyy into vzz minus vyz square, that is going to be, okay, so what it will be is I think this is going to be 72 into 72 minus, I think, 36 whole square. So this is 72 square minus 36 whole square. So this is certainly going to be positive. So it's going to be greater than 0. Right? Yes. Okay, so it's greater than 0 at this point. So this implies it has maxima or minima. Okay, but Vyy is less than 0. So this tells you that 18, 18, this has the maximum, okay, by second derivative test. Now, this implies, so what is the maximum value is V at 18, 18 is going to be 108 minus 2y minus 2z times y times z. So that is the equation. So you have this is going to be 108 minus 36 times 18 into 18. So this is going to be totally is going to be minus 8 minus 72 to 18 into 18. So that's going to be some 11,664. Okay, that's going to be in terms of inches. Okay, so this is a maximum volume of the acceptable box, rectangular box, with respect to the condition. Okay, right. I think we can stop here now. Okay, if you have any question, you can ask, or we can close here.
Sir, why we have discarded 0, 0 there?
0 because volume will be 0, right? If x
Oh,
equals
yeah.
to 0, y. Okay, if volume is 0 means there is no box. You are not giving any box to the delivery company. Is that clear?
Yes, sir. Yeah, I got it.
Oh. Oh, we have class till 9:45. I thought that's 9:30 till 9:30. Anyway, I have completed concepts today, which I was to. So that tomorrow we will see the Taylor's theorem. Okay, and we'll try to look at the application of the Taylor's formula in favor of deciding the this which we have mentioned today. Okay, second derivative test. We have mentioned some based on mentioned some theory that if the sign of that the determinant of the Hessian matrix is greater than 0, then it will be in the same way all the direction, either downward or upward, but provided the time allows, of course, we'll see. I've already given you hint today, but I think I may mention the very specific form. That at least I will do that. Okay, fine. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Yes, sir.